All right. Welcome everyone to the Casio webinar, over and over again, a look at composition of functions using cool problems on the Casio Prism. My name is Tom Biattini. I am a authorized Casio educator in ACE. I teach at Glen Rock High School in Glen Rock, New Jersey. And I'd like to share some things with you that tie into the new core curriculum content state standards, which is something that everybody is going to be held accountable to, at least in most states, in the years to come. And on the first page of your handout, you can see that we have a list of the core content standards that we will be addressing.
One thing, Tom, I'd like to interject really quickly. Just for those that are in attendance, I want to make sure that they understand that when they are in one of our webinars, we do mute all of the attendees, and any questions that can be typed into the question pane, which I, as facilitator, will be responding to, and then I can share those in turn with you. And just to briefly introduce myself, I'm Nathan Austin. I'm the Curriculum and Online Training Manager for Casio. And so, again, thanks for letting me butt in there, but if I have any questions, I'll be sure to throw them your way.
You feel free to butt in at any time.
Okay, and I'll be handing control of the screen over to you.
Okay.
There you go. So you'll just want to make sure you click on Show Your Screen.
Okay, so here we go, showing my screen. As I was saying a little while ago, on the second page of the handout, we have the core content standards that are addressed. And some of the things that we want to pay attention to here is the idea of being able to decontextualize and contextualize problems and situations so they can be represented mathematically. One of the things we want to be able to do is take real-world situations in the form of a word problem and be able to model those mathematically as well, because at the heart of the structure of algebra is the 5 mathematical representations. We have tables, we have graphs, we have verbal descriptions, we have pictures, and we have equations. I think I got them all. And that ties into modeling. And also, if we take a look at the very last bullet at the bottom of the page, the idea of building functions. So we are describing a relationship between quantities. We want to be able to describe explicit expressions or recursive sequence, recursive process, and then the idea of performing a composition of functions so that when we take an input value, from it we can get an output value. So if you would flip to the third page of the handout, we have a question at the top that's for the end of the session. It's on the cover, from the cover screen. What is the first term of the sequence in the sequence of numbers in the calculator screen on the cover? And what is the rule for the sequence? So what we're trying to do here is we're trying to go backwards in the process of generating a sequence. So we'll come back to that later, time permitting. Regarding the first example, we have a sequence of numbers, 5, -6, -17, -28, -39, and so on. And what we want to be able to do is represent this sequence as a composition of functions. Now, looking at the function box, what we are trying to do with the arrows is show what we would use as a pictorial representation of a composition of functions. We have an input value. We put it into the box. The box contains an operation that does something, that performs some operation on our input value, and we get an output value. Then from that output value, what we are going to do is recycle it and make it an input value and do the same process over again. So in this particular case, what we have is we have a pattern that is being repeated, but we also have a composition of functions. So what you want to do right now is go to the main menu with all the icons. So here we have the main menu, and highlight the graph icon, which is number 5. Press number 5. And if there are any formulas there, you want to delete them. But now that we are on Y1, the next thing we want to do is type in the equation x minus 11, the equation that you saw in the function box. The reason why we are doing this is because the difference in the terms are, the difference between each pair of terms is going to be 11, and to get from the second term to the third term, or the third term to the fourth term, we are going to be subtracting 11. So we want to key in x minus 11 followed by execute. Now, this represents the function rule that we had in the box that you saw on the previous page. Now what we want to do is press the menu key and go back to the Run Matrix menu. So highlight number 1 on the main menu and press execute. Now, in order to generate that sequence of numbers that we had on the previous page, what we need is we need a seed value. And the first term of the sequence was 5. So now we type in the number 5 followed by execute, and it is now stored on the home screen. If you would turn the page to the top of the 4th page where you see step 6, what we want to do right now is get the second term of the sequence, because 5 is the first one. So what we need to do is press the vars key followed by F4 for graph, and this allows us to find variables that we are going to be using through graphing. We want to call up the equation that we stored in Y1. So now we want to press F1, which gives us the Y value on the screen, followed by the number 1. So we're telling the calculator that we're going to be using the equation stored in Y1. And now we want to put something in parentheses, because since Y equals screen is a function screen, we can perform an operation using any one of those functions on any number that we choose. The number we are going to choose is in the calculator already. That's the number 5. But since it is the previous answer, in order to develop the sequence, what we need to do is not type in the number 5, but type in shift answer and then close off the parentheses. So what we are telling the calculator to do right now is take the value of 5 and subtract 11. Now, we are set to go. Press execute. 5 minus 11 is negative 6. So that's the second term of the sequence. We press execute again. We have the third term of the sequence. So what we have done to get negative 17 is take Y1 of the answer. And we can continue this process to find all the terms of this particular sequence, which has been generated through a composition of functions. Now, if we wanted to get since we have the third term, which is negative 17, if we wanted to get the fifth term, what we could do is Y1, parentheses, Y1, parentheses, shift, answer, and hit the right parentheses twice. And what we're going to be doing is subtracting 11 2 times. Okay, so we've subtracted 11 2 times. Negative 17 minus 22 is indeed negative 39. So now this clearly indicates that we do have a composition of functions going on. So now if we wanted to find what would happen using this rule, if 56 was the seed number, we have to type in 56, press execute, and now 56 is the first term, and now we need to count how many times we are going to use y1. So we will repeat the process again. y1 of our answer. So if 56 is our first term, then we want to do this 9 times. Press the execute key 9 times to get the 10th term. So here's the second term. Here's the third term. Here is the fourth term. Here is the fifth term. Here is the sixth term. Here is the seventh term. Here is the eighth term. Here is the ninth term. And we now have the 10th term. This could have been obtained by typing y1 9 times and having 9 sets of nested parentheses, but it's much easier to type it once and then press the execute key. Are there any questions so far?
Nope. So far, everything's going well.
Okay. All right. So now, problem number 1, underneath the questions, we are given the sequence 1, 5, 13, 29, 61. And in order to generate our sequence that we have here using a composition of functions, we have to identify what the seed number is. And the seed number is always going to be the first term. So now what we need to do is type in 1 and press execute, so that is stored. But we need to get our rule. So in order to get our rule, we need to go back, press the menu key, choose graph, and we have to delete what we have stored in y1. So we're going to do that and delete the formula. And in this particular case, we have to think of what we are doing to each term in order to get the next one. So this is going to require a two-step process. It's not perfectly arithmetic and it's not perfectly geometric. What we are going to have to do in order to get from 1 to 5 and then from 5 to 13 is take each of those previous values, 2x, take each of those previous values, we have to double it, and then we have to add 3. So we are storing the equation 2x plus 3 to y1. Now that is stored to y1, what we can do is press the menu key, go back to the Run Matrix screen, and now we can bars, graph, choose y1 as we did before of our answer. And we've generated the second term of the sequence. And now we have to find out what the ninth term is. So if we're going from the second term to the ninth term, we need to do this 7 more times. So here is the third term, here is the fourth term, here is the fifth term, here is the sixth term, here is the seventh term, here is the eighth term, and as you can see, the numbers are getting big very quickly. Here is the ninth term, and we are done. Now, there is a connection with these numbers to our formula. All of these numbers, if we go back to the graph screen, our formula is 2x plus 3. Each of these numbers that we have in our sequence are powers of 2 with 3 subtracted. Now, give it some thought as to how we have gone from generating powers of 2 what part of our equation generates the powers of 2, and then we get an expression with 3 less than that. So some food for thought, something to think about at the conclusion of this webinar. And you can email me with any comments or questions regarding that. But it'll be a stimulating conversation for students to ask them, why does this work? Now, sequences and numbers, like we have done, are good examples to get people warmed up. But one of the best things about composition of functions is they can be used to model real-world problems, as we have here with question number 2 regarding Cece's credit cards. Cece has been having some difficulty. She has $1,500 in outstanding balance, and then has been laid off unexpectedly from her job, so she has no income, and as a result of having no income, she can only make the minimum payment. And what we want to do is find out how we can get the balance down and how long it's going to take her to pay this card off if it's going to be only the minimum monthly payment for however long she's unemployed. So what we need to do is we need to come up with some kind of rule and think in terms of the seed number. So in this particular situation, her seed number, let's go back to the menu screen, our matrix. Her seed number is going to be 1,500 because that's what her current credit card balance is. So we're going to type in 1,500 and enter. So it's now stored. And now we want to go back to the menu screen. And we have to come up with some kind of rule. Let's delete the equation that we have stored in Y1. And the way this is going to work is she's going to be making the monthly payment on the same day every month. So what happens is she's getting charged an interest rate for the entire month. So if she makes a payment on January, if she has a balance of $1,500 on January 1, she's going to be paying interest for the entire month of January. Then on February 1, she is going to be making a payment. So we have to take the balance, which we're going to represent with the variable x, and add on to that 1.5% of x. So we can do x plus 0.015x. And then, after that month in which she's accumulated interest, she's going to make the $50 payment. So we have to subtract 50. This expression that we have stored in Y1 can be simplified, but for our purposes, we want to see where the 1.5% interest comes into play. So now we've got our seed number and we have our rule. And what we want to do now is find the balance on the credit card over the next 6 months. So let's press menu, go back to run matrix, and we have to think of the 1,500 as being month 0, because that's the balance on the account when she's been laid off. So now we are going to repeat the process from before. We are going to vars, graph, choose Y1, shift answer, and press execute. So because of the interest and then the $50 payment, she's only paid down about $27.50 of her bill. So this is the balance after the end of the first month. So now we can find the balance, let it be here, for 6 months. So we press, this is month 2, this is month 3, month 4, month 5, month 6. Now, one of the things that banks do is in situations like this, when they are dealing with fractions of a penny, because they don't want to lose money, they always round up. So we could have set up this equation that we had stored in Y1 using the rounding feature in mode, but for our purposes, we just want to generate the sequence here and not get into the finer details. The goal is to get students, in this particular case, to understand exactly what the process is. So, are there any questions so far regarding this problem?
Not so far, Tom.
Okay. All right. So now we've gone out 6 months, and now we want to find out how long it's going to take for her to get her balance under $1,000, because that's a fairly laudable goal. So we are going to keep pressing the execute key and count in our mind how many times we've done it so we can find out the answer to question C. So we have 6 months. She has the balance here of $1,328.69. Again, we're rounding off to the nearest whole. We're rounding up to the nearest cent. So we have 7 months, 8 months, 9 months, 10 months, 11 months, 12 months, 13 months, 14 months, 15 months, 16 months, and it looks like after 17 months, she's going to be able to get her balance under $1,000. Now, does this mean that it'll take another 17 months for her to pay off a credit card? Well, we have to take a look and see. It might be longer. I mean, it took her 17 months to pay off $500, but one of the things that's happening is, since we have a smaller balance, she is accumulating less and less interest. So if we keep pressing the execute key, we have it 17 months, 18 months, 19 months, 20 months, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, the end is in sight, 39, 40. So at the end of 40 months, she has a balance of $7.63. So a little more than 3 years it took her to pay off this bill. And now all she has to do is just pay $7.63. So we've racked up 40 months worth of $50 payments plus the $7.63. So the total amount of money that she had to pay back was, well, let's see, we have to do 40 months times 50, so 40 times 50 plus the $7.64 that she has outstanding still, and that'll be her total payback on the amount of money that she had outstanding on the credit card. So she had to pay back $2,007.64 and racked up $507.64 in finance charges. This is a rather powerful problem because it brings home to students the power of a composition of functions, doing repeated process over again, and also every student wants a credit card as long as someone else is paying the bill. So what we want to demonstrate to them here is that about 1/3 of her original balance was what she ended up paying back in finance charges. Now, there is a variation on this problem with number 3. If you flip the page and take a look at problem number 3, it is the same scenario but with a slight variation. Cece's aunt is going to help her out. And based on what Cece's aunt has told her, she is going to help Cece as long as she is making regular monthly payments with a payment of $200 every 3rd month. So Cece will pay $50 a month, and then every 3rd month the aunt will give Cece $200 to pay the bill. So let's go back to, well, first, since we're here on the home screen, let's seed our sequence again. Let's seed this. We're going to be starting off with $1,500. And now we want to go back to the Y equals menu. Now what we're going to do here is in Y1 is keep CC's payments. And then what we're going to do in Y2 is we're going to type in a function that represents how much the ant is paying. So in this particular instance, we are going to use a very similar equation. Let's combine the like terms that we have here and have 1.01. Well, I didn't want to do that, did I? I just delete, well, I can retype what I did before. I'm going to simplify that first equation. I didn't want to delete 1.015x minus 50. Again, my apologies for deleting that. And now in Y2, what I want to do is I want to do 1.015x minus 200. And then execute. Okay. So on the top line in Y1, we have CC's payments. And then in Y2, we have the payments she is going to be making with the money her aunt gave her. So if we go back to the Run Matrix menu, we have our sequence seeded. So this is the $1,500 is the outstanding balance on CC's credit card at the current time. So now we want to find out how much our balance is going to be for the next 6 months. So what we are going to do is we're going to call Y1, so vars, F4, Y1, and we are going to choose our previous answer, which is 1,500. So we are going to get, for the first 2 months, we are going to get the same values we had in the previous problem. So the $1,472.50 and $1,444.59 are the balances for months 1 and 2. And now, for month 3, we have to change our function because CC's aunt is going to be making a payment for it. So now we want to have Y2 of our answer. Wow. Helps make a big dent in things when the rich aunt kicks in some money. So at the end of 3 months now, our balance is $1,266.26. So on months 4 and 5, CC's going to be making payments. So what we are going to do is use Y1 again. So Y1 of our answer. Or actually, now let's just do Y1 of our answer 2 times and see how the numbers work out. So here's month 4, here's month 5, and then for month 6, because her aunt is paying her bill in multiples of, in months that end in 3, or multiples of 3, we want to do Y2 of our answer. I didn't want to do that. I didn't mean, no, so let's delete that expression. Parentheses, shift answer. Okay, so that drops things quite a bit now. Before, in the previous problem, it took her about 17 months to get the balance under $1,000, and here after 6 months, things are looking pretty good. So it looks like on the 7th month, if we do Y1 here, I didn't mean to do that, Y1, parentheses, shift answer, and execute. So after 7 months, she's going to be under $1,000. And if we keep repeating this process of, this is 7 months, this is 8 months, and then do Y2, here's 9 months, and then Y1 2 times. Well, we're going to do Y1 2 times, but we're going to put it on the same line. So we're going to take care of months 10 and 11 because it looks like she's not going to pay off the balance. So Y1 of, oh, let's delete that. I got carried away with myself there. Y1 of our answer. So here's months 10 and 11. At the end of 11 months, the balance is $688. And now we can do Y2 for 12 months. $498. And then what we're going to do now is we are going to use one of the features of the Casio Prism that is rather useful. We can scroll up and use previous commands that we have entered, and now what I'm going to do is press Shift followed by the number 8, which allows me to clip or copy a line. So now I'll type F1, and then what I'm going to do is press F1 again to jump to the bottom of the screen. And now I am going to paste that expression, Y1 of our answer, into the box where you see the cursor flashing. Oops, something happened there. What did I do wrong? I did something wrong. All right. Where was I here? Okay, this was all right. Okay, my apologies everyone for getting fancy. But what I'm trying to show you kind of leads into the next thing I wanted to demonstrate with this problem. Because what we can do is I'm going to clear everything out that we have here. And start anew. And what I'm going to do is reseed the sequence, or reseed the situation that we have with 1500. Okay, that wasn't supposed to happen, but I guess it did. Don't pay attention to that. Now we're at the bottom of the screen, which is where we want to be, so I want to reseed the sequence. Okay, and now what we want to do is we want to get the balance every third month after the ant makes the payment. So we want to demonstrate this by doing vars graph Y2, which represents the third month. And then we're going to do Y1, which represents the second month. And then we're going to do Y1 again, which represents the first month. So what I'm doing here is I am getting, let me delete here, make sure I have the correct, oh, I forgot something. That's what I forgot. I got to get in. I got to get my answer in there. All right. So we have to do an answer, shift answer. And get one more parentheses over on the right-hand side. So the Y1 of our answer represents the first month. That's in the red parentheses. Inside the blue parentheses would represent the balance at the end of the second month. And then Y2 of everything represents the balance at the end of the third month. So if we press execute, we get CC's balance at the end of 3 months. If we do this again, and this is where the power of composition of functions is extremely useful and is demonstrated. Here's our balance at the end of 6 months. That makes sense with what we had before, because we said at the end of 7 months she would have her balance under $1,000. Okay, so now at the end of 9 months we got her balance. At the end of 12 months she's got it under $500. At the end of 15 months, it's $219. And then it looks like at the end of 18 months, the bank owes her money. So it looks like it will be somewhere around 16 or 17 months where she'd be able to pay off the credit card. But by using the command and going every 3 months, we were able to skip terms of our pattern and enable us to reach the desired result a little bit quicker and get an idea of how long it would take for Cece to pay off her bill. Are there any questions so far?
Not a question, but a comment. Someone pointed out that this is actually a pretty good example. This has to do with a credit card, but this is also could apply nicely to a mortgage when you're making like that extra payment or something like this.
Oh, absolutely.
It'd be another good example. I think a lot of adults could benefit from that concept as well.
Oh yeah. Paying down the credit card, making the extra payment on the mortgage, you can put things to rest a heck of a lot sooner in a situation like this. Okay, now I made a mistake. What I probably should have done is I should have used problem number 4 before we did problems 2 and 3, because this is the type of situation that a lot of students run into. They go out for lunch and they have a coupon. And they might have an ID card, and certain things happen whether or not they have, they can get certain discounts with a coupon or by using their ID card. So what we have here is we have Jen and Priya going to the Hamburger Shack for lunch, and they both have a 50-cent coupon, and they also get a 10% discount by showing their student ID card. And we have to figure out how much the girls are going to be paying. So in order to figure out how much Jen paid, she got the value meal for $5.49, so 5.49, we're going to type that in. And the first thing she did was she used the coupon, so we have the minus 50 cents. So after the coupon, she's now got the bill down to $4.99. But because she has a student ID, she will save 10%. So what we can do now is we can either type $4.99 or take our previous answer. Let's do $4.99. And then subtract 10% of $4.99. Minus 0.1 times 4.99 and press execute. So she's going to end up paying $4.49 if she uses the coupon and then gets the discount. Now Priya, on the other hand, her server rang up the value meal and then the coupon, I'm sorry, and then the discount for the ID, and then she used the coupon. So what we want to do is we're going to have the $5.49 and we're going to subtract 10% of that. Okay, so this is the price with the ID discount, and now we've got to subtract 50 cents from this, so $4.94 minus 50 cents. She saves 5 cents compared to Jen. Now, the thing we want to do is take a look at representing each of these situations as a function. So if we wanted to represent this particular situation as a function in terms of C of X to deduct 50 cents or more discount, what we can do is press the menu key and go to graph. And before I continue, one of the things that I could have done, referring back to the last problem involving Cece, I could have entered in y3 our composition of functions. So I could have thought of y3 as that expression that we used with the sequence of y2s and y1s in the previous problem. It would look like this. Let me just show this to you quickly. y2, parentheses, y1, parentheses, y1, parentheses, and now what we're going to be doing is we're going to be using x as our variable here. So x, and then 3 right parentheses, and if we wanted to think in terms of y3 after we seeded our sequence, that would have worked as well. But now that we're on to another problem, and we're not talking about credit cards, we're talking about burgers, fries, and shakes. Let's delete everything we have here. And finish our problem with Jen and Priya. So what we want to do in y1 is write a function that represents deducting 50 cents. So that's going to be x minus 0.50. And then in y2, we want to have a function that represents taking 10% off the price. So we could have x minus 0.10x. Now, to represent this as a composition of functions, what we can do is, well, let's make things a little bit easier. Let's simplify what we have here in y2, since we do have like terms. Let's make this 0.9x. Now, if we wanted to represent this as a composition of functions in which we are going to have c of d of x, what we want to do is we want to store what we have in y2 in place of x in y1. So y3 would then be expressed as 0.9 x minus 0.50. So what we have in y3 is going to represent the cost of our value meal when we do the student discount first and then take off the 50 cents. So let's go back to the Run Matrix menu and see if that does indeed check out. So we'll go to 1, and we're going to do 549 because that's the cost of the value meal. That's what we want to evaluate. And then we are going to check out y3. So do what we did before. We're going to choose y3, and we're going to use our answer. And as it turns out, that was a situation for Priya where she had the student discount, 10% off, and then the coupon. What I could have done in this particular instance, instead of using the answer, I could have done y3 and typed in my 549, the price of the value meal, and still gotten the same thing. But the reason why I used the answer before was to show how we need it if we're going to be performing a repetitive process, a composition of the same function over again. But since here we have y3 representing a composition of two separate functions, we can use the value that we are storing for x. Are there any questions so far?
Nope, not so far.
Okay. So now the question is, and I think it's pretty obvious, which server used the c of d of x function, and I think that was Priya's server. Now, Nathan, how much more time do we have?
Somewhere, anywhere 10 to 20 minutes as
Okay.
you're comfortable.
All right. Okay. All right, we only have plenty of time to work through most of problem number 5 here. All right, now, one of the places where students and adults deal with this idea of composition of functions, although it's a little known fact, is with purchasing tickets to events, sporting events, concerts, and there is a tremendous markup for tickets if they're bought secondhand, third hand, and so on down the line. Now, being from New Jersey, in New Jersey they have certain laws regarding scalping tickets to in-state events. So if you purchase a ticket and want to sell it to somebody, under the law, the maximum you can sell it for is 20% above the face value of a ticket. So if I purchased the concert ticket from a scalper, he can only charge me 20% above the face value that he paid. However, if I in turn wanted to sell it to someone, I could charge 50% above the value of what I paid for the ticket. And this does not include any fees or service charges. Now, if we are thinking in terms of representing the cost of a ticket after the 20% markup, what we want to do is we want to go back to the graph screen, and we want to delete our functions that we have stored here. And in y1, we want to represent the equation y1 equals 1.2x to represent the 20% markup. Then in y2, we want to represent the cost of a ticket after it's been sold, when it's been sold secondhand. So that's going to be 1.5x. Now our two functions are stored. Okay, so in a situation like this, what we want to do is we want to take a look and see what the price of a Bon Jovi ticket is going to be after it's been sold, has face value of $100, after you've purchased it from a ticket broker. So what we want to do in a situation like this is we want to represent our function as a composition of the first two. So we want to do here bars, graph, y2 of y1 of x. Press execute. So this represents, y3 represents the cost of a ticket after it's been purchased and then sold secondhand. So now, what we can do is we can go back to our menu. I'm sorry. Go back to our Run Matrix menu, and what we are going to do is find y3 of $100. So bars, graph, y3, and in parentheses we're going to put 100 and press execute. So the price of that ticket is going to be $180. Now, the way this would work if I was going to do this step by step would be is if the ticket was purchased at face value, that's our y1 equation with the 20% markup. So we would do y1 of 100, that's going to be 120. Now, if we are doing the 50% markup of the 120, what we would do is we could do y2 of 120, or we could do our answer, but let's do 120, because that's the number we're working with, and we still get 180. So this demonstrates that y3 is a composition of the first two functions. And if we wanted to continue this process, all right, if you're the fifth person, we're looking at letter D here, if you're the fifth person to buy the ticket, what's going to happen is, let's use our seed value here. We are going to do y1 one time. So we're going to take this step by step. We know it's going to be $100, but we need to use our answer. So F1 of 1, and we are going to do shift answer. So this represents the price the second person is going to pay. Now, in order to continue this, we've got to do y2 3 times. So y2 of our answer. So there's the here we have third person, fourth person. The fifth person is going to pay $405 for that $100 ticket. Are there any questions about the process we have just gone through?
No, excuse me, no questions so far.
Okay. Now the food for this thought on this particular problem was given to me as an aside here when I purchased theater tickets for my wife's birthday to see Spamalot, and I was very willing to pay $135 per ticket online. And when I got the tickets in the mail, they had a $15 face value. And the thing that came to mind was, how many times did the tickets change hands before I eventually got them in my hands? So I've been looking into the process by which this sort of thing works in the state of New York. So if we are going to be doing something like this, if we're looking at letter E here, which is the Madonna ticket, and we want to, and you're going to be the fourth person to purchase it, what we need to do is we need to do the process we did a little while ago, and we need to use the y1 function once. So let's use 200 to get things going. This is our seed value, and the markup for the first sale is y1. Got ahead of myself here with my parentheses. Shift answer. And this is going to be the price the second person would pay. And now we got to do it 2 more times with y2. So let's show this on one distinct line. So we got y2, parentheses of y2, parentheses, shift answer. So that $200 Madonna ticket, if you're the fourth person down the line, is going to cost you $540. Now, the thing that makes this interesting, which would tie in very, very well to an Algebra 2 class here, is the problem I have set up here in letter F, which ties the idea of composition of functions to an inverse function. So what we need to consider is we need to look back at working backwards. So if you are the first person to purchase a ticket, you're paying the 20% markup. This means what is going to happen is we have to look at the reciprocal of the 20% markup, or 1.2 times x, or 5/4. Actually, I made a mistake on that, didn't I? 1.2x is the same thing as 6/5 times x, so our reciprocal of that is going to be 5/6. So when you don't have that 20% markup, the original price is 5/6 of the price that was paid by the person on that first stage. So let's go back to our menu and go to the graph screen. And in Y1, what I want to do now is I want to represent our inverse function. I'm going to clear this out. I'm going to delete these terms, and I'm going to put in a fraction. That didn't work. Okay, excuse me while I undo that. I want to, let's see, I want to insert, and I want to insert a fraction. No, that still didn't work. Delete, delete. Let's just delete the whole line, and we're going to do 1 over 1.2 is the same thing as 5/6x. So we're going to have a fraction here, and we're going to do 5, 6, x. Now, the reciprocal of 1.5x, or 1.5x, is 2/3. So I'm going to, let's just, for argument's sake, let's exit here, and we're going to delete y2, and we're going to put in a fraction here and make this 2/3 x. And execute. So what we're going to do right now is we are going to use our functions that we have stored in y1 and y2 in order to find out what the face value of that Lady Gaga ticket was. So let's leave the y = screen and go to the Run Matrix menu, and we are going to, since we are thinking in terms of the fourth person, we have to go backwards 2 times in this particular instance to find the face value. So the question that we have here is, how many times do we need to use y1, and how many times do we need to use y2? So what we need to do in this particular instance is, since there was a 50% markup twice and a 20% markup once, and we're working backwards from the 675, we've got to use what we have stored in y2. And let's go back and look at our y2 value again, which is 2/3 x. We've got to use our y2 value 2 times. So now what we're going to do is bars, graph. Well, I'm sorry, I forgot something. I need to type in my 675. So let me do that right now. And so now we want to find out how much the ticket cost for the third person. The 675 is for the fourth person. So now I want to do y2 of our answer. So the third person paid $450. The third person in the chain. The second person in the chain paid $300. Now, the first person, okay, you've got to think in terms of the 20% markup. So now we need to use our expression from y1. So the first person ended up paying $250 in this particular instance. So the face value of this Madonna ticket that was sold for $675 was a little bit more than 1/3 of that, which was $250. This is a concept or an idea that I think has an extremely valuable use for classes at the Algebra 2 level and beyond. And some of these problems could probably be done in an Algebra 1 class if the students are given the proper training in terms of the notation with the calculator that is very, very user-friendly. But the way we teach composition of functions, as it's shown in most textbooks, is very, very dry, and it's mostly symbolic. And I think providing students with examples like these and problems like these will stimulate interest and will help them get a better understanding of what composition of functions, and in the case of this last particular problem, what inverse functions are about, because they long to have credit cards, they deal with coupons and discounts from student IDs, and they all want to have credit cards. So concerts, credit cards, and coupons, some of teenagers' favorite things, I think can be used to help make the mathematics come alive with the idea of composition of functions and in some cases inverse functions. I hope you have enjoyed this webinar, and if you have any questions, please do not hesitate to contact me, and I will get back to you with a response as soon as I possibly can. Again, thank you very much, and have a good evening.
Thank you very much, Tom. I was thinking as you were wrapping the concert tickets up, you know, it occurs to me that one of the things students really struggle with is this idea of an inverse function and how to undo what they did. You know, for instance, if you added 20% on,
yeah,
you know, what's the reverse? They want to remove 20%.
That's right.
And this would be a great way for them to play with that concept. And, you know, if y1 was adding 20% and y2 was subtracting 20%, why does that not work? And so good examples. I've enjoyed this a lot.
Okay.
So really quickly, I just want to wrap it up also by sharing with anyone who's with us that we have this online course available. The calculator that Tom is using this evening is our relatively new Prism color grapher. And if anyone's interested in following up with that, looking into it, we have an online course that you can take to learn more about it. It has some trial software that you'll download at the web address you see on your screen. And for the time being, as of, let's see, early May 2012, finishers of the course are being given either their choice of the Prism emulator software or the calculator. At least this is for educators specifically. In the past, we've had a promotion where students or teachers were getting the calculator, and we've had to scale back that promotion just because of a huge response. So, in any case, thank you for joining us this evening. Thank you again very much, Tom. It was nice following along.
Okay.